we will resume with our discussion on nonlinearity, basically graduating beyond a simple sigmoidal perceptron. In the last class, we saw how one issue with the perceptron is that it doesn't ensure margin separation. So we saw the support vector machine classifier as an alternative that provides sufficient margin. Prior to SVMs, we've also seen how nonlinearity could be attained nonlinear classification could be attained using kernels, right? And we've seen how we could kernelize both in the supervised setting and the unsupervised setting. Supervised, we have seen logistic regression, perceptron, ridge regression. Unsupervised, we have k-means, PCA, and so on. Now we will move on to neural networks, and neural networks will initially motivate as another tool for nonlinear classification. We will also see a notion of capacity, how powerful a classifier could be. Very briefly, we will touch upon something called VC dimension, and then we will move on to deep learning. We will be referring largely to sections of this book, Deep Learning by Yoshua Bengio. I have uploaded this book on Moodle. So, very quickly recap: nonlinearity via kernelization, for example, logistic regression, where we saw at length how we get this very interesting form for the decision function as well as for the objective in terms of a linear combination of dot products or similarities measured with respect to examples in the training data set. So, perceptron, kernel perceptron, logistic regression, kernelized logistic regression, and now we move on to neural networks, and throughout we keep referring to some of the previous discussions to see connection. So, what is interesting about neural networks is that they serve as universal function approximators. So, kernels, you have to design a particular form of kernel, for example, polynomial kernel. Let's take the following setting. Let's say my points are like this. These are my two classes. Okay. Now, if I have to separate the positive from the negative class, I'll have to choose the right form of the kernel to be able to do this. Polynomial kernels may not give me separability in this case, right? Whereas neural networks give you a framework which serves as a universal function approximator. So, it's possible to design a neural network under the framework such that you are able to attain separability for this somewhat arbitrary case. The data is separable, but just not linearly. So this is an interesting property. I am going to very briefly touch upon how you get this. Again, I will not be able to entertain too many questions on this just because this requires separate discussion. So with a single hidden layer of a sufficient size and a reasonable choice of non-linearity, including the sigmoid, hyperbolic tangent and RBF unit, one can represent any smooth function to any desired accuracy, both separation and regression. So what universal function approximation here specifically is referring to is that I have this x and an arbitrary dependent variable y. I should be able to approximate y to any desired level of accuracy. All you have to do is make your neural network very sophisticated. And we know that accuracy you could measure with respect to sum of squared errors. The greater the required accuracy, the more hidden units are required. Okay. Let's quickly tinker with this neural network, and let me begin with a regression. Okay, so I need to refresh. Still showing classification. Okay. Anyways, you could play around with this, and you can give a slightly challenging data set to regress upon, and you can with a single hidden layer, but with an arbitrary number of neurons, you can find that the functions could be fitted reasonably well. But she's still showing a classification data set. I don't know why. Do I change it to regression? Anyways, you can play around with it. So you can basically approximate functions to any desired level of accuracy. Of course, there is no free lunch. There are several free lunch theorems, no free lunch theorems, which means the more accuracy you want, the more hidden units are required. So that is the tension. So as your desired accuracy increases, the number of hidden units you require will also increase, and that's exactly what no free lunch theorem try and codify this trade-off. This trade-off between accuracy and complexity. So the problem is as follows: given data points x1 to xm, some possible class choices. We are going to now focus more on classification. Though several of the discussions here will easily extend to regression, and we wish to generate a mapping from x to c1 to ck and get class labels y1 to im, where each of y1 to im belong to one of c1 to ck, and we do this using a series of mappings. Now we have motivated this earlier when we talked about perceptron, but now you're going to see this in action. Okay, and let's see this in action here. Very interesting URL where you get to play with many of these. So you can create this f and g's and h and increase the complexity of each of these. So let's go back to classification. Okay, so when I don't have any hidden layers, right, basically then I don't have any of these y's or z's. I'm directly going from x to c1 to ck, but then moment I add these intermediate layers, there's one layer I've added the f and now F and a G, added one more, I have an F and a G and an H. I mean, this is exactly the setting that our simple depiction refers to. And here are two challenging data sets. Okay, so this is a challenging data set, as you can see on the right. You need to separate the blue from the orange using an F and a G and an H, and we're going to try training it. I'll use sigmoid as activation to begin with. This is what we are familiar with. There's a learning rate. Very gradually. So very gradually you can see that it still took some time. The training loss is decreasing steadily. Test loss is taking even more time to reflect. So we have chosen 50% of the data to be training and 50% of this to be test. Reduce the size so that you can see everything. Okay, and what you see here are flows to the network. There's a forward flow through the network which lets you draw the classification, the classify boundary, and there is a backward flow from the data to the network to help adjust the parameters of the network. So there's a constant flow both ways, and you've seen there's a kind of saturation here. I mean, it doesn't seem to be decreasing further. It hasn't really figured out the nature, right? But let's try and increase the number of hidden layers. Do we see a difference? Let's check. Again, it's taking some time. So after suddenly you find that the network starts registering the nature of the separation. Though it isn't necessary that every network configuration gets you separation. Okay, so yeah, this has been quite some time. I've added more hidden layers. So I've actually added the number of these intermediate mappings, but that doesn't seem to have helped so far. I mean, just increasing the number of intermediate layers is not really helping so far, right? In fact, yeah, didn't help at all. Now let me change the activation to something else and see what happens. Okay, so some other activation function has learned faster. Of course, it has still not learned a good classifier. It just has a small band covering the blues. The rest is all yellow or orange. So this is not really the intended separation. Okay, so you can play around with it. I think with a TANH you might get what you want. But I'll go back. We'll keep referring to this very interesting application playground. So what are these other nonlinear activation functions which I just showed? Right. So if you have F is G times W transpose phi x, or in general we'll avoid using phi or very often. We'll just write it as Fx is G times W transpose x. Now what are the forms G can take? So if you look at this playground tensor flow, this allows G to be which of the following? You go back, you can see that the activation can be TANH, sigmoid, linear and ReLU. What are these? TANH, sigmoid, linear, which we are all familiar with, and ReLU. So sigmoid and linear we are all too familiar with. TANH and ReLU, what are these? We'll see that. So in fact, I'm going to quickly show you what these might look like. Okay, so these are some plots I made. T is tan H, R is ReLU, S is sigmoid. You can ignore this P for the time being. In fact, I'll delete that. Okay. So you'll find that sigmoid are all too familiar approximation to the step function is here. What do you observe about sigmoid? Let's say you contrast that with tan H. So this is a form of tan H. What's the difference between tan H and sigmoid? Yes? Range. So sigmoid is between 0 and 1, tan H is -1 and 1. What else? Well, it is the range, but it also is interesting that at 1 they tend to kind of agree. I mean, the trend is very similar, right? So tan H seems to be more sloped or sigmoid. So they are achieving the same, I mean, they are kind of achieving the same value at 1 at a similar space, but allowing more flexibility in the negative range for tan H. So tan H has a faster rate. It is more sloped. Okay, and ReLU, what do you observe about it? R. Yeah, that's what I'm saying. It's a higher, greater slope. What about ReLU? What do you observe about ReLU? The blue one. So the blue one is basically here. Flat at 0, it kind of shoots off at 45 degrees. So it tends to tries to align itself with sigmoid at 0, but it is unbounded above. And below 0, since the negative values of the input, it just flattens out. So ReLU's full form is rectified linear unit. Okay. So there's another function called softplus. Yeah, let me just show the equations here first. So step function we all know, sigmoid 1 plus e raised to 1 upon 1 plus e raised to minus s. Rectified linear unit is just max of 0 comma s, right? So this is just s if s is greater than or equal to 0, the 45 degree line. There's one more function, soft plus ln of 1 plus e raised to s. This is not implemented in or not reflected in the user interface of playground or TensorFlow. But here's how it looks. Okay, this is the soft plus. What do you observe about soft plus? Differentiable version of ReLU. So ReLU, why would it be interesting? Why would ReLU or its differentiable version soft plus be ever interesting? So what is the kind of limitation of sigmoid or tan H? That they always flatten out, right? Now if you consider a cascade of models, I mean, isn't it natural that sometimes you might want the activations to be large? See, the other sigmoid and tan H, the activations are always subdued, -1 +1, but magnitudes could matter, especially when you have lots of layers, right? I mean, we immediately saw the moment we switched to ReLU, this guy was able to learn something more meaningful than in the case of sigmoid, right? I mean, let's go back to sigmoid for this data set. I mean, it didn't learn anything at all. I mean, we waited for too many iterations. There was nothing happening here. So you can see the test loss is changed. I mean, the test accuracy and training accuracy, nothing is changing. They're like 50-50. But the moment I switch the activation to say ReLU, Okay, so now ReLU emits signals which can be very large in magnitude, right? It's not clipping off the signal. So that can have an advantage. So the question is, sigmoid has a Bayesian inference interpretation, right? What about ReLU? So it's not necessary that everything gets mathematically justified in the world of neural networks. So that's my first advice. But at the same time, we have seen that Lasso, surprisingly, right, had a mathematical interpretation. It had something called a Lidstone prior. So ReLU can be also thought of. I mean, it's the only issue is unbounded. It's unclipped. So otherwise, ReLU also gets clipped at 0. So think of ReLU as associated with some kind of a Lidstone prior. So that's possible. Okay, so soft plus we just noted is differentiable version of LU. So of which, so differentiability is with sigmoid and soft plus of these 4. Tan H I had not shown here, or did I? Okay, we had tan H here, right? So I did show tan H here. Tan H could is also another option. Or minus 1. There's a minus 1 too. This is a form of tan H. Okay, it has a feeling of a rescaled and more quickly changing sigmoid. Okay, so yeah, so, you can check out this URL. Now there are also a couple of other interesting activation functions which you will come across. Recall that we talked of logistic extension to the multi-class. Like logistic regression was 2 class. We said we can handle multi-class. How did we do this? We talked about this, right? How did we handle multi-class? K minus 1 parameters. So for k equals 2, we have just one parameter. For in general k, we have k minus 1 parameters, where those parameters were associated with classes with 1, 2, WC1, WC2 and so on, WCK minus 1. For classes C1 to CK minus 1, this was our form. Right? The regular kind of logistic form, the sigmoidal form for the class 0, and for the last class, you don't have anything in the numerator. Basically, you don't have E, W is 0 for the kth class, right? Effectively. So 1 upon 1 plus, the denominator remains the same. Now Softmax is equivalent to that multi-class version, and Softmax is a popular and equivalent extension to multi-class. It's called Softmax. Okay. So what you do is you associate parameters for all the k classes, all the this k here. For k classes, you associate this parameter, and now you have more than the required number of parameters. You can show that you don't need so many parameters. You can show that this is equivalent to the previous form. Yeah, I put that in tutorial 7, and that's very simple. So C equals 1 to k, probability of y equals C given x Okay, so this is softmax. Okay, and let's just recall sigmoid for two class. The probability of class one as e raised to minus w transpose x divided by 1 plus e raised to minus w transpose x. So this one, think of this one as being obtained by setting w for one of the classes to 0. Okay. Sigmoid for two class. And softmax for k class. So yeah, in your tutorial 7 you can just show the equivalence between these two. It's very trivial. As I already hinted, it's just by getting one of the w's to 0, setting one of the w's to 0. That's how e raised to 0 will give you this one. Okay, I'm going to now talk about this universal function approximation, the strength of neural network, viewed very quickly through a tool, a measure called VC dimension. I hinted to VC dimension earlier. I'm now going to just quickly tell you what VC dimension is about. I have lots of extra slides for you guys to look at, but let's try and understand how do you measure the non-separability, right? How much non-separability can a classifier give you? I'm sorry, how much separability does a classifier have in terms of linearity and non-linearity, right? So for example, in tutorial 3 we saw this. Given n Boolean variables, there are how many Boolean functions? 2 raised to 2 raised to n, right? So of these, how many can a perceptron classify? How many functions can a perceptron approximate? So we saw this, that for n equals 2 it's 14, for n equals 3 is 104. How did you guys compute these? We just took the cases, right? So there was no closed form. So in some sense, for n equals 2, it's 14 divided by 2 raised to 4, right? It's 14 divided by 16. That's the extent of separability that you can achieve using perceptron. Likewise, you can compute this ratio for n equals 3 and you will find that the ratio really shrinks. There's one way you can measure. You've done this. The second aspect is you can look at the cardinality of largest set of points that can be shattered. Now what does this mean? So I give you the classifier, let's say in 2 dimensions. This is a linear classifier, 2 dimensions. Now I can, let's say I have 2 points, right? Point 1, point 2. I give this a plus, I give this a minus. I'm able to separate them. Okay, I say the family is of linear classifiers. I give you these two, plus and minus. Can I separate them? I can find a linear separator. I move this point somewhere else. The minus point I moved here. Can I separate them? So I'm playing a game. I give you these 2 points. You are able to draw a separator. Can I do this for any 2 points and any 2 assignment of labels to those 2 points? I can, right? Now suppose I give you 3 points. Can I separate the positive from the negative for any 3 points and any 3 assignments of labels to those 3 points? This I can. I change the label. This I can. Okay, so that's your job, that's not my job. I will separate. You have to Give me those points. So he is giving me these 3 points minus. Okay. So he's smarter. He says no, I don't like this. Now I'm in a fix. How do I separate? I can't use a linear separator, right? It's fairly easy to see that. I mean, they are collinear, by the way. Forgive my bad plotting, but they are linear, right? So the cardinality of largest set of points that a function can shatter, where shattering is what? A function is said to shatter a set of points if for all assignments of label to those points there exists a W such that FW makes no errors. So the cardinality of the largest set of points that FW can shatter is its VC dimension. Now, is that a bad thing that, so in this case, for 3 points, for some given 3 points, particular assignment I am not able to shatter. So what's the VC dimension for this linear classifier in R2? In R2, your F is linear classifier. Question is, what is the VC dimension? As per this definition, VC dimension in R2 where F is a linear classifier. Question is, what is the VC dimension? By that definition, is it 2? Is it 3? For 2 points. Now, have you mentioned anywhere that for every or any pair, any set of n points? Let me illustrate with an example in 3D and then you can come back. 3 points. 3 points can be shattered using linear classifiers. I mean, I have shown you how these 3 points, for any configuration of these 3 points, I can shatter. But I can't for one particular set of 3 points. But there exist other sets of 3 points for which I can classify. Is that correct? I mean, for these 3 points under all labelings I am able to classify. There exists a set of 3 points in R2 which can be linearly separated for every possible, and here the number of possible labelings is 8. Labelings of those 3 points. So there also exists a set of 3 points for which for some labeling I can't separate. For this labeling I can't separate. Now what will be will that define my VC dimension or this one? I want the class to think. What is, if you want, I'll go back to my definition of VC dimension. A classification function is said to shatter a set of points for a set of points if under all assignments. See, it's about all assignments. The claim is not about all points. N points under all assignments, I am able to basically separate them. So cardinality of the largest set of points. Are we claiming that largest set of points of all set of points under that, all set of n points? No. There should exist one such set of n points, right? If there exists any one such set of n points, then VC dimension will be, then what can I say about VC dimension? Will be at least n. Now this doesn't bother us. This is not an issue because we have positive mu somewhere else. We know that for these 3 points, under any possible labeling, I will be able to separate. Okay, so this is what we are concerned with, not this. Is that clear? By the definition. So VC dimension of linear classifier in R2, what do you think it will be? 3 or greater than equal to 3? Well, it is actually greater than equal to 3 as per this example. But we can show that for 4 points I can't do it. Right? I can easily jinx you for 4 points. We will not bother with this case anymore. But if I give you 4 points, I give you a nice set of 4 points. I am not as tough master as him. So I just give you nice points. But any labeling you should be able to separate. Are you able to separate? I mean, this labeling you are able to separate. This labeling can you separate? You can't. You want a linear separator, but you know, any linear separator you try, there will be some mixing up. Not possible. Okay, so you can show that. In fact, in this case, VC dimension is exactly equal to 3. Okay, now we will not get into the proof. I mean, this can be proved, and I have given you a lot of extra notes for this. It's optional. The proof is not part of our syllabus. This intuition is good enough. Okay, so similarly, you can show that 4 points can be shattered using axis parallel rectangles. If my classifier is not just this linear separator, but axis parallel rectangles, box, I can draw these rectangles, but they have to be axis parallel. Then I can show that 4 points can be shattered also. These 4 points can be shattered. Plus, plus, minus, minus. How will I separate? Which of these cases? Which one? Without rotation I can't. So it's an interesting thing. It's all about existence. So this is not the most friendly set of examples. I'll give you another set of examples. Plus, plus, minus, minus. This can be, right? Again, we are only concerned with existence. Okay, let me draw it in blue because blue is about existence. Red is about not impossibility. This is fine. 4 points can be shattered using axis parallel rectangles. Okay, you can show that VC dimension, while it's greater than or equal to 4, is actually equal to 4 as well. Okay, so in general, let me ask you some more questions. Quiz time for all of you. So if f is a threshold interval, answer this question. If f is a threshold interval in R, what do you think is the VC dimension? Very simple question. Threshold. So I give you just a straight line, and I say, well, anything less than that is negative or whatever. Anything greater than that is positive. So what's the VC dimension? 2 points. It's a threshold. So 3 points, not possible. Okay, because 3 points. If I give you plus, minus, plus, how will you draw a threshold? Separate the positive from the negative. Okay, so VC dimension less than or equal to 2, it's actually 1. So let me show it even for 2 cases. So what we have assumed is that the threshold is fixed in terms of what what should be in the left or what should be the right. So anything to the left should be negative, anything to the right should be positive. We fix that semantics. When we say threshold, that's what we mean. And when we draw boxes, we mean is anything inside the box is a particular class. So yeah, I mean you will be able to classify for positive, negative this way, but the moment you make it negative, positive, this threshold will fail. Okay. So depends on what your classifier is. Classify here for us means that less than threshold, less than theta is positive and greater than equal to theta is negative. That's the, let's say that's the meaning of a threshold. Yeah. Yeah, all I'm saying is threshold you learn, but what is the class to the left and class to the right, that we are fixing. No, we did. I mean, we implicitly did. We said that anything inside the box is positive. I mean, you can have another set of classifiers where you learn, where even the label on the left and right you assign. I'm just saying for this particular simple threshold classifier space, it's 1. Now you can change your classifier space. Nobody says this is the only threshold classifier. This is a very specific form of threshold classifier. Yeah. Yes, exactly. So his point is, if you also decide which side of the classifier should be positive, which should be negative, then it will be 2. Then the VC dimension will be 2. Okay. That's what I initially was tempted to. If you can also decide class label below and above threshold, VC dimension. So moment somebody asks VC dimension kya hai, you have to say what is the space of classifiers. You have to ask this question back. For F as an interval classifier. Now again, I'll specifically say that interval, inside interval, class is positive, outside interval, class is negative. Okay, I'm fixing it here. What's the VC dimension? So inside interval, class is positive, outside is negative. If I make it this way, can I shatter? For 3 points. For 3 points, can I shatter? No. Inside interval, the class is positive. I mean, with some fixed notion of class, inside the interval, I will not be able to shatter 3 set of points. 2 I can. Okay. For F as perceptron, what's the VC dimension in R2? We have already seen that. For F as perceptron, what's the VC dimension in R2? It is, what is it? Sorry, I can't hear. 3. For F as perceptron in Rn, what do you think with the VC dimension will be? No, it's about existence. So if I flip the labels here, see, if I flip the label here, my threshold can change. Yeah, only fix the class. We are saying that anything to the left of the threshold is positive, anything to the right is negative. That's it. But where the threshold is, that otherwise, if you fix that, then it's like fixing the classifier. I mean, we are trying to fix the family of classifiers, right? We are trying to say, well, here's the family. From there you choose. I mean, if you can choose 2 electives out of 2 electives, then what is the meaning of an elective, right? You need more choices. So we are saying, well, there's a family to choose from. The threshold is one family. The threshold plus the side is another family. Yeah, that's why for a threshold classifier, where we have fixed side for class, the VC dimension is exactly 1. So for 2, this doesn't hold. That's all we are saying. So you can't, for 2 classes you can't shatter. For 2 points. Yeah, but depends, right, whether you have fixed the, we can maybe take this offline, but depends on whether you are fixing the class inside the interval or not. The interval is not being fixed, the threshold is not being fixed in these cases. Otherwise, what is the meaning of choosing a classifier, right? So what for f as a perceptron? Here we don't have any fixed side of the class, obviously. Fixed side of perceptron is a particular class. But what is this VC dimension? Can you extrapolate from R2 where the VC dimension is 3? For Rn the VC dimension will be n plus 1. Okay, so see extra slides for the proof. I will not get into this any further. Yeah, so there's a very formal proof. I'll put the slides. Intuition is basically R3, similar thing you had to extend there. Yeah. Okay, so neural networks. Why are neural networks interesting? Because they give you this very high expressive power. Again, I want to draw your attention. What you are doing as you add these additional layers in the middle, right? You are increasing the ability of the classifier to be able to shatter, and because you increase the ability of the classifier to be able to shatter, you possibly are able to shatter for a larger set of points as well, right? So that's what we saw here. But let's take a simpler example. Let's take these three and let me. Okay, so this is just no hidden layers, and I'm going to try and classify these points. Certainly doesn't look like a good case for linear, and this is exactly what we saw earlier, right? I mean something like this. This is the same case. So are we able to classify? Yellows are on diagonally opposite side, blues are on diagonally opposite side. You are not able to classify. It doesn't matter how long you keep trying. Okay, and I've used ReLU. You may say, okay, I'll change it to sigmoid. It will not change. Story doesn't change. I mean, one part is the positive side is here. Then all these are turning out to be negative, which means error is 50%. But now let me add a hidden layer. I can also add more hidden. I can add one also. Let's just add one. Let's see what happens. So I just added one hidden layer. Not doing a great job. One. Let me add two. Somebody may say it's because of sigmoid. Sigmoid doesn't seem to be very useful here. How about ReLU? Oh, sorry. I have one, but I'll just increase the number. Okay, so you've got for some value number of hidden layers, you're able to get this desired linear stability. I mean, it's like error is almost zero. It has got the concept, right? So with 4, I mean, let's try and reduce it and see if we get it. Well, for 3 also, for 4 also we get it. But I reduce it to 3. I'm able to do it. I reduce it to 2. It messes up. So this is what we were also referring to the universal approximation. So what all is expressive power owing to? It's because of non-linearity in activation functions and a cascade of non-linear activation functions, both. Actually, if you use, let's try using linear, you will see the difference. Okay, linear, and let's say I increase the number of hidden layers, linear. With linear, I mean, you keep adding, nothing will change. it's still silly, right? So nonlinearity of the intermediate activation functions is important, because cascade of linear will only give you linear. It's like matrix multiplication. You will get, 10 matrices multiplied together is just a new matrix. Okay, by the way, this is also a problem in tutorial 7, that the cascade of linear will, it's all, some of these are very common sense observations, but I kind of articulated them as a tutorial problem. Okay, so therefore these nonlinear activation functions, the variety starts making a lot of sense. There are also others like Riki, leaky, ReLU, max out, hard tanh, absolute value rectification. So again, in the textbook, which is on Moodle, section 6.2.1, you can look at other activation functions. So now I think you got a fairly good idea why this kind of can work, and now we'll get into the details of how to make it work. So far it was all about why. Yeah, we can. We want to see what happens with linear, sigmoid. How many? Decrease the number of neurons here, make them all similar size. Okay, so it hasn't done a good job so far, but I think it will get it. It's still a bit lost. Now almost got it. Yeah, it's got the concept. It's a matter of time. We'll get it very close to perfect. This is what you wanted to see, right? Okay, so what exactly happens? It's really a complex function of the number of data points, right? It's a little hard to say. There are a couple of theory papers on the behavior of neural networks. Maybe I'll point you to some of them, but each of them gives you some, make some assumption on the distribution of the points. Generally, without making any assumption on the distribution of points, it's very difficult to make a claim. What exactly the neural network layers do. But I can give you a high level idea. What the first layers do is look at local vicinity, right? So basically, as you proceed, you can see in these nodes, right, what's exactly happening. These neurons are basically giving you an idea of what space they are capturing. So this seems to be capturing. You remember PCA? We talked about eigenfaces. So think of these as getting some dimensions of the separable desired separation. So this says blue patch here, this says blue patch here in these two locations. This is a slightly faded version of this with the blue patches here. So I think more or less this guy is what is dominating. So this is dominating where the blue patches will be, right? So it could be that some of the neurons are playing the role of determining some aspects of the class labels. In general, as you proceed ahead in the neural network, the observation and the expectation is also that you are capturing higher level features, because the class label is the highest level feature. The original points are the lowest level. So what we would express is going from the lowest level of abstraction to the highest level of abstraction. That is expected. But what exact highest level of abstraction would depend on the architecture of the network, would also depend on the distribution of the points. But is that making sense? So a good question. Okay, so in section 6.1 of the textbook, there is a mention of 4 design choices in a neural network: the input layer and the hidden layers. Okay, what the hidden layer should be, how many hidden layers should be, how many nodes in each hidden layer, that's a design choice. what the nature of the output layer should be is a design choice. What the loss function should be is also a design choice. And what are the loss functions we have seen so far? Yes? What are loss functions we have seen so far? Cross entropy, likelihood. Likelihood is not a loss function. Hinge loss. Did we see hinge loss? We also saw sum of squared errors. Okay, so the choice of the loss function. With respect to hidden layers, number of hidden layers, and number of nodes per hidden layer. Okay, and again showing you those activation functions, binary, logistic, tan H. This tan inverse is also often used, and you can see the general nature of each of these. ReLU I talked about. There is also parametric ReLU, which says, well, a ReLU just suddenly flattens out at 0, I mean in the negative interval, but parametric ReLU says that, well, the slope will decrease, but it will not just flatten out. Okay, and ReLU and parametric ReLU are not differentiable everywhere. In fact, binary step is also not differentiable everywhere. Okay, then there is exponential linear unit. Softmax I already mentioned is a differentiable approximation to the ReLU. And here are the derivatives. You can also visualize the derivatives of the activation functions. So you will find that some of these activation functions are very flaky or very sensitive, fragile in their derivatives. So for example, tan H, its derivative peaks at 1. Now peaking of a derivative can be an issue. I mean, derivatives becoming too small or too big can be an issue. Why? Yeah, wait, so that then the step size becomes important, and you can get numerical precision errors. For example, if the is too small, then it may just vanish because of multiplicative effects, right? Or if it's too big, it can explode. Okay. Okay, so here are some interesting visualizations. We'll refer to these further, but now let's start building our neural networks. Here's a simple OR using perceptron. OR, right? X or Y is 1 if X is 1 or Y is 1 and 0 otherwise. I have used this minus 0.5 as a threshold. This is the minus 0.5 is a weight, it's the value of B, I think. It's the value of B, theta equals half is threshold. So in a sense, this is a threshold for the step function. Okay, we have used a step function here. What I want you to do is design for AND. This is OR. How would you? Is this correct? Any mistakes here? If you think this is correct, if you validated it, design one for AND. So one is the weight associated with input X. One is also the weight associated with input Y. So the learnable parameters here are W x which equals 1, Wy which equals, turns out to be 1, value of b. Now theta will not be learnable. Let's not learn theta. We chose the step activation function and we'll just fix it. Okay. So design one for AND. If you're done designing for AND, then try and design a neural network for XOR.